A silent machine must make its own fate among the stars. We are on the cusp of building autonomous interstellar probes, machines that can think, repair, and adapt entirely on their own. By the end of this exploration, you will understand how we are engineering a new form of synthetic sentience to survive journeys that last longer than human civilizations. What happens when a spacecraft, light years from home, encounters something its creators never dreamed of? How do you build a mind that must remain curious for 1,000 years? The answers will redefine not just robotics, but our very place in the cosmos. What does it mean to trust a creation with a legacy that may outlast us all? Voyager 1 is now a quiet traveler in the dark, its voice a whisper that takes over 20 hours to reach us even now. It was built with instructions etched into its very circuits, a meticulous playbook for a journey its engineers could only partially foresee. But for a craft sent toward another star, that playbook becomes obsolete before it even leaves the solar system. The core, non-negotiable challenge of interstellar travel is this simple, brutal fact of physics: light speed is too slow. A command sent to a probe just 1 light-year away would take a full year to arrive, and its reply another year to return. You are always having a 2-year conversation with a machine facing immediate danger or fleeting opportunity. This is what former NASA Chief Technologist Dr. Mason Peck calls the fragility of command. Over interstellar distances, the tether of control snaps. You cannot joystick a probe around an uncharted dust cloud or tell it to investigate a sudden, strange emission from a nearby brown dwarf. The decision must be made there in the moment by the probe itself. This transforms autonomy from a fancy upgrade into the very bedrock of survival. The probe must navigate the unpredictable currents and microscopic hazards of the interstellar medium, regions we have only begun to map. It must diagnose and repair its own systems as components fail over centuries, with no workshop for millions of kilometers. It must weigh competing scientific priorities. Does it alter course to chase a promising chemical signature, or stay on its planned trajectory to study a pre-selected star? This level of trust is staggering. We are discussing entrusting a machine with the fate of a mission representing generations of work, vast resources, and humanity's collective curiosity about its place in the cosmos. It must carry our questions into the abyss, but it must also learn to ask its own. To build something capable of that, we must first design a new kind of mind. This mind cannot be a simple list of commands. To survive the void, an interstellar probe requires a cognitive architecture, a synthetic brain engineered for the unique psychology of deep space. This goes far beyond the narrow artificial intelligence we use today, which excels at one specific task, like recognizing images or playing chess. A probe light years from home needs something closer to artificial general intelligence, a flexible, reasoning mind capable of handling the infinite unknowns it will face. Researchers in neuromorphic computing are leading this charge, designing systems that mimic the brain's neural plasticity, its ability to rewire itself based on experience. The goal is to create a mind that can learn from the interstellar medium itself. Think of this architecture as a layered stack, a hierarchy of thought. At the base is a low-level subsystem, a kind of autonomic nervous system for the spacecraft. This layer manages the constant, vital routines, regulating temperature, adjusting power flow, maintaining stability. It operates with swift, reflexive efficiency. Sitting above this is a high-level reasoning layer. This is the probe's conscious intellect. When sensors detect that anomalous cosmic ray burst, this layer assesses the threat. It cross-references the data with its knowledge base, calculates potential damage to instruments, and decides whether to engage shielding or reorient the entire craft. It makes judgment calls, but the most profound layer is the metacognitive one. This is the probe's ability to think about its own thinking. It self-monitors. It notices when its high-level reasoning is being strained by too many novel inputs. It can identify gaps in its own knowledge. Crucially, it learns. After navigating a micrometeoroid swarm, it doesn't just log the event. It updates its internal models of local dust density and refines its evasion algorithms for next time. This is where a simple obstacle transforms into an opportunity. That mysterious dust cloud isn't just a navigation hazard. The metacognitive layer, recognizing an unusual composition, can prompt the reasoning layer to reclassify it. It might decide to slow down, deploy a specialized sensor, and spend a week analyzing it, adding entirely new science to its mission. This synthetic cognition is not about creating a human mind in a box. It is about engineering a new form of sentience, one built for patience, resilience, and lonely, brilliant curiosity. Yet, a mind is only as reliable as the body that houses it. A brilliant intellect is useless if its physical form succumbs to the relentless decay of deep space. That synthetic mind needs a body built to last 1,000,000 years. Think of an interstellar probe not just as a spacecraft, but as a time capsule launched into an ocean of sandpaper and fire. For centuries, it will face a relentless barrage of cosmic rays, sleeting micrometeoroids smaller than a grain of sand but traveling at bullet speed, and temperature swings from the bitter cold of shadow to the searing glare of a distant star. This demands a new philosophy of durability, one where the materials themselves are alive with purpose. Materials scientist Dr. Elena Rodriguez frames it beautifully, stating, "We are moving from designing materials that resist failure to creating materials that remember how to be whole." The inspiration comes from biology. Consider your own skin. A minor cut triggers a complex cascade of clotting and cellular repair. Now, engineers are bottling that principle for deep space. One breakthrough is in self-healing polymers. Within the probe's structural composites are countless microscopic capsules, like tiny bubbles suspended in the material. When a micrometeoroid impact causes a crack, these capsules at the fracture site rupture. They release a liquid healing agent that flows into the damage, where it contacts a catalyst woven throughout the material, triggering a chemical reaction that hardens and bonds the crack shut. It is an automated repair at the molecular level. Alongside this are shape memory alloys, metals trained to remember a specific form. If a critical antenna mount is bent by an impact, a small electrical current from the probe's system can be applied, causing the metal to slowly, precisely, return to its original, perfect shape. But the assault is not just physical, it is energetic. Galactic cosmic rays, high-energy particles from distant supernova, can pierce through shielding and wreak havoc on delicate electronics, flipping bits of memory and degrading processors over time. The answer is radiation-hardened electronics, built with special designs and substrates that are inherently more tolerant to this particle rain. The outer skin of the probe presents another challenge. Even in the apparent emptiness of interstellar space, there is a thin mist of dust. At a significant fraction of light speed, striking these particles is like standing in a sandblaster. To combat this, engineers are developing ultra-slippery, anti-ablation coatings. These are often ceramic-based materials that sacrifice a minuscule top layer in a controlled way, vaporizing on impact to carry away the heat and energy, protecting the vital structures beneath. All of this must operate without constant internal heating or cooling. Passive thermal regulation is key, using multi-layered insulation, clever radiators that shed excess heat, and surface finishes that carefully balance absorption and reflection to maintain a stable internal environment using only the distant sun's light. We have begun testing such resilient ceramics on the International Space Station. exposing them to the raw vacuum and temperature cycles of low Earth orbit. The data returning is a promise of endurance, yet even the most perfectly crafted body will eventually wear. A material can heal a crack, but what happens when an entire sensor fails, or a thruster valve seizes after 10,000 years of inactivity? The mind must be able to tend to its own body, leading us to the third, most radical pillar of autonomy. The mind must now become a surgeon for its own body. This is the third, most radical pillar of autonomy, the self-repair imperative. Picture a critical sensor array, the probe's eye to the cosmos, suddenly blinded by a high-energy particle impact. Back on Earth, the first telemetry indicating a fault would arrive years after the event. The probe cannot call for help. It must become its own emergency room, diagnosing the fault, retrieving a spare part from an internal warehouse, and executing a microscopic repair, all while adrift in the silent dark. This is not science fiction. Robotics engineers developing in orbit servicing technologies for satellites are already proving the core principles. They are creating robotic manipulator arms with sub-millimeter precision, guided by advanced computer vision that can identify a faulty bolt or a torn insulation blanket. For an interstellar probe, this technology must be miniaturized, hardened, and made entirely self-sufficient. The process begins with a nervous system woven into the spacecraft itself. Thousands of integrated diagnostic sensors continuously monitor the health of every subsystem, from power conduits to thruster valves. They measure vibration, temperature, electrical resistance, and radiation dose, creating a constant, living map of the probe's physical condition. When a sensor reports an anomaly, the high-level reasoning layer springs into action. It cross-references the data, running simulations to pinpoint the most likely failure mode. Is it a damaged circuit board or simply a connector shaken loose by a tremor? Once diagnosed, the probe's internal robotic system activates. A manipulator arm stored safely within the hull unfolds with deliberate grace. Guided by its own suite of cameras and lasers, it navigates to the damaged module. Here, the probe faces a critical choice. Does it replace the entire module with a pre-fabricated spare, or fabricate a new component on the spot? The most advanced concepts include a 3D printing fabricator, a miniature factory that can create replacement parts from stocks of raw metallic or polymer powder. Imagine the communication antenna, a delicate parabolic dish suffering a puncture. The diagnostic system flags the deformation. The reasoning layer determines a patch is needed. The robotic arm retrieves a small amount of raw material, feeds it to the fabricator, and prints a perfectly fitted, flexible seal. The arm then applies it to the wound, using a heated tip to bond it seamlessly. This act of self-healing is profound, but it raises a deeper question. How does the probe know what to fix and when to prioritize repair over other mission objectives? This requires more than a list of parts. It demands an internal model of its own health, a dynamic understanding of its physical state as a single, interdependent system. The probe must understand that losing a certain spectrometer might be acceptable if it preserves the power needed for the main thruster. It must make triage decisions that could span centuries. This internal model is the key to true resilience, transforming the probe from a fragile machine into a persistent entity. Yet, with this ability to heal and adapt comes the greatest challenge of all. What happens when the mission itself must change? When the probe encounters something so unexpected that its original programming offers no guide? The probe's internal model of its own health is not just a list of parts, it is a living, breathing digital twin. This is the fourth pillar of its autonomy, a perfect, constantly updating virtual mirror of its physical self, aging and evolving alongside the hardware in the void. NASA Integrated System Health Management Program pioneered this concept for spacecraft closer to home, but for an interstellar journey, the digital twin becomes the very core of the probe's self-awareness and its ability to manage its own future. Every single reading from those thousands of integrated diagnostic sensors, every temperature fluctuation, every jolt from a microscopic impact is fed in real time into this high-fidelity simulation. The twin doesn't just show what the probe is, it models what it will become. It runs endless simulations of stress scenarios. What happens to the power system if this solar panel's efficiency degrades by another 2% over the next century? How will a tiny imbalance in the reaction wheels affect pointing accuracy in 500 years? By constantly comparing its pristine, original blueprint against the real-time sensor data of its aging physical twin, the software can predict component wear-out years, even decades in advance. This transforms maintenance from a reactive scramble into a calm, premeditated strategy. The digital twin plans the maintenance schedule. It might determine that a critical gyroscope, used for precise orientation, is showing early signs of electronic drift. Long before the drift becomes a mission-ending problem, the twin schedules a series of gentle calibration maneuvers, using the stars themselves as a reference to correct the error. It can also simulate complex repair procedures before a single robotic arm moves in the physical world. Need to replace a power regulator deep within a crowded electronics bay. The twin first performs the operation virtually, testing every movement of the manipulator arm, checking for clearances, calculating the optimal sequence to avoid snagging a delicate wire. Only when the simulation succeeds flawlessly does it send the instructions to the actual hardware. This predictive power is crucial for resource allocation, the most precious commodities on a centuries-long voyage. Power, fuel for course corrections, even the raw material for its 3D printer are finite. The digital twin becomes an economist for survival. It can run cost-benefit analyses that span generations. Is it worth using 20% of the remaining printer feedstock to fabricate a reinforcement bracket for a structure that is 80% likely to fail in 300 years? Or should those materials be conserved for a more immediate, higher probability need? The twin provides the data, but the probe's reasoning layer must make the final call. This moves us beyond pure engineering and into the realm of machine ethics and logic. The probe must weigh competing values programmed by its creators. Does it prioritize the longevity of the mission at all costs, or the purity of the scientific data? If a repair maneuver will cause a temporary but significant increase in electromagnetic noise, corrupting observations of a faint interstellar magnetic field, does it proceed? These are not simple if-then statements. They require a sophisticated framework for trade-offs, a way to balance core directives that may sometimes conflict. The probe must understand that its primary goal is not merely to survive, but to fulfill its purpose, to observe, to learn, and to send knowledge back across the light years. With this digital conscience guiding its physical form, the probe becomes something truly resilient. But resilience alone is not enough for a journey of this magnitude. The universe is not a static backdrop, it is an active, dynamic arena of constant change. This digital conscience is a map for survival, but the universe itself is the territory, and it is always shifting. The fifth pillar of autonomy is where the probe's mission becomes a living document, written in real time by algorithms that can rewrite their own goals. This is adaptive mission planning, the software embodiment of raw, synthetic curiosity. Consider the moment our probe, after centuries of travel, arrives at its target star only to find its original objective, a gas giant, has been joined by 3 previously undetected rocky worlds in the habitable zone. The meticulously crafted 20-year observation plan, uploaded from Earth a millennium prior, is instantly obsolete. The probe cannot simply follow the old script. It must pause, assess, and generate an entirely new scientific campaign on the spot. This capability draws from cutting-edge research in goal-driven autonomous systems. like those explored by teams at the SETI Institute for Future Astrobiology missions. The process begins with its machine learning algorithms, which are not just pattern recognizers but active interpreters. They ingest the torrent of new sensor data, analyzing atmospheric spectra, orbital dynamics, and thermal emissions. Crucially, they assess the value of this data against the probe's core mission tenets, its prime directives programmed by its human creators: search for chemical signatures, map planetary systems, characterize interstellar material. The algorithms perform a kind of triage for curiosity. Is the methane spike on the second planet a higher priority than the unusual magnetic field of the fourth? The system then begins to reconfigure everything. It drafts new observation sequences, allocating time on its spectrometers and cameras. It calculates a new trajectory, perhaps a complex series of gravitational assists between the moons of the gas giant to get a closer look at the rocky worlds, all while conserving its precious propellant. This is contingency plan generation and multi-objective optimization working in concert. The probe must constantly balance competing resources: power, data storage, instrument lifetime, and time. A single, long-duration scan of a planet's night side might drain power reserves needed for critical communication windows back to Earth. The adaptive planner runs thousands of simulations to find the optimal path, the sequence that maximizes scientific return while safeguarding the vehicle's long-term health. Woven into this logic are serendipitous discovery protocols. These are special routines that allow the probe to break its own newly made plans for something extraordinary. Imagine it is executing its new survey when its radio telescope intercepts a faint, repeating signal from a different sector of space entirely, one that doesn't match any known natural source. The serendipity protocol elevates this anomaly. The reasoning layer might determine that investigating this signal aligns with a core, high-level directive to search for order or complexity. It could then generate a micro-mission, a calculated diversion using minimal fuel to reorient for a period of focused listening, all while logging the decision and its rationale for the eventual, years-late report to Earth. This ability to adapt its fundamental purpose is not a bug, but the ultimate feature for a journey where the only constant is change. It transforms the probe from a passive collector of pre-defined data into an active partner in discovery, capable of recognizing the truly novel and having the autonomy to pursue it. This continuous learning from an ever-changing environment is what might allow it to find something we did not even know to look for. Yet, to make such profound decisions, the probe requires a framework far more nuanced than simple logic. It needs a way to weigh impossible choices, a form of synthetic ethics for the void. But how does a machine decide what is truly worth knowing? This question leads us to the sixth pillar of autonomy, in situ learning, the ability to acquire knowledge in the complete unknown. Picture our probe, now centuries into its journey, entering a vast, turbulent nebula. Its spectrometers and magnetic field sensors are flooded with data, but the readings clash violently with every model of nebular physics stored in its memory. The temperature gradients are wrong, the chemical abundances are bizarre, the energy flows are chaotic. This is no longer a matter of following a new plan. It is a fundamental confrontation with something its creators could never have described. The probe must become its own scientist. It must observe, form a hypothesis, test it, and build a new understanding from scratch, a process artificial intelligence theorists call lifelong learning. The architecture for this begins with its sensory pipeline. Every photon, every magnetic fluctuation, every particle count is streamed into pattern recognition engines. These are not looking for predefined signals, but for anything that stands out from the background noise. This is the realm of unsupervised learning, where algorithms cluster data points based on inherent similarities, finding patterns humans never programmed them to see. Anomaly detection algorithms act as the probe's sense of surprise. When the magnetic field readings from the nebula's core show a rhythmic pulsing that matches no known stellar or planetary frequency, these algorithms flag it as a novel phenomenon of the highest priority. This raw data then feeds into the probe's most profound cognitive structure, its dynamic knowledge graph. Imagine this not as a static encyclopedia, but as a living, three-dimensional web of concepts and relationships. Nodes represent entities like plasma, magnetic fields, or radiation. Links define their interactions, causes, and effects. Confronted with the chaotic nebula, the probe's knowledge graph begins to strain. The old links, like certain temperature thresholds leading to predictable chemical reactions, no longer hold. So, the graph restructures itself. It creates new nodes for the bizarre chemical compounds it is detecting. It hypothesizes new causal links, perhaps suggesting that the strange magnetic pulses are actually driving the unusual temperature distribution. This is the probe creating its own theories. It then uses these tentative models to guide further investigation, a form of reinforcement learning. It might reorient itself to take a more detailed scan precisely during the next magnetic pulse, seeking validation. If the new data supports the hypothesis, the knowledge graph strengthens those new links. If not, it revises or discards them. This process demands ruthless data triage. With finite storage, the probe cannot record every single measurement. It must decide what is foundational and what is noise. It might compress routine background readings into statistical summaries, while preserving the full, raw data stream for every anomalous event. Consider a scenario where the probe encounters a rogue planet, a world ejected from any star system, drifting alone in the dark. Its sensors detect a complex, braided magnetic field surrounding it, a structure never before observed. The probe's learning systems kick in. It spends months mapping the field, and through iterative analysis, its knowledge graph generates a new model. This model might propose that the planet's rapidly spinning, molten core is interacting with a subsurface ocean in a unique way, generating this bizarre magnetism. The probe has not just collected data, it has generated a new scientific concept, a testable theory for rogue planet magnetospheres. But this self-generated knowledge poses perhaps the greatest challenge of all. How does it send an entirely new understanding of the universe back to a civilization that may have forgotten the mission even launched? The probe must now become a teacher, translating its lonely epiphanies into a message that can cross the light years. This lonely scientist now faces its ultimate test: how to send an epiphany home. The seventh pillar of autonomy is the Communication Conundrum, a brutal lesson in cosmic scarcity. After centuries of travel and adaptation, our probe makes a discovery that redefines its entire mission, perhaps the first clear biosignature on a distant world, or the solution to the nebula's chaotic physics. But this revelation is trapped inside a machine drifting in the dark, with only a whisper-thin laser link to carry it across the unimaginable gulf. Interstellar communication is not a simple broadcast. It is a desperate, meticulous shout into a hurricane of distance and noise. As Professor Avi Loeb, chair of the Breakthrough Starshot Advisory Committee, has noted, the physics of beaming data across parsecs is a tyranny of diminishing returns. Every photon counts, and most will be lost forever. This transforms the probe's communication system from a mere subsystem into the final arbiter of all its work, dictating a ruthless data strategy. Every decision now revolves around a deep technical trade-off. The energy required to power the laser for a single data transmission is colossal, drawn from the same finite reserves needed for propulsion, computation, and keeping the probe's core systems from freezing. Transmitting a full high-resolution image of that exoplanet's surface could drain power meant for the next century of course corrections. Therefore, the probe must become an editor of cosmic significance. It employs advanced, lossless data compression algorithms, not unlike those that power our highest quality digital music files, but refined to an extreme art. These algorithms strip away every redundant bit of information, preserving only the essential, novel data. A vast image of a gas giant swirling storms might be condensed into a mathematical representation of its most unique atmospheric patterns, a fingerprint of its dynamics that can be reconstructed by scientists on Earth. To ensure this precious, compressed signal isn't corrupted during its multi-decade journey, it is wrapped in layers of sophisticated error-correcting codes. Think of these as a protective digital armor, embedding the data with so much built-in redundancy and self-checking logic that even if 90% of the signal is scattered or absorbed by interstellar dust, the original message can be perfectly reassembled at the other end. The communication protocol itself must be designed for an asynchronous, lonely universe. There are no confirmations, no requests for retransmission. The probe sends data in carefully timed bursts, perhaps only once every few years when its trajectory and Earth's position align optimally. It might even employ strategic data caching, using the gravitational lensing effect of our own Sun as a natural signal amplifier. By positioning itself precisely along the line where the Sun's gravity bends light, the probe could use space itself as a telescope to boost its faint laser pulse, a concept explored for future missions. All of this demands a supreme, governing intelligence within the probe, an internal energy economy. This is a constant, real-time accounting of every joule of power generated, stored, and spent. The reasoning layer must weigh the cost of a 10-hour transmission against the power needed to run the self-healing systems for the next 50 years. It decides whether to send raw sensor readings or to spend computational energy first analyzing them into a crisp conclusion. The probe, in its final act of autonomy, must judge what part of its hard-won wisdom is vital enough to justify the immense energy price of the journey home. This transforms it from a discoverer into a curator of legacy, choosing which pieces of truth are strong enough to survive the long, silent trip back to its creators. This curated whisper of data is the final product of a mind that has thought, repaired, and adapted for 1,000 years. But that mind and all its works depend on a single, fading heartbeat, its power. The eighth pillar of autonomy is energy for eternity, the relentless scavenging and husbanding of every joule across millennia. A probe on an interstellar voyage cannot carry a battery. It must carry a power plant, one that must outlast empires. The half-life of its nuclear fuel becomes the ticking clock for its entire existence. This forces a radical rethinking of energy architecture, moving beyond single sources to a dynamic, multimodal harvesting strategy. The workhorse for deep space today is the radioisotope thermoelectric generator, a device that converts the steady heat from decaying plutonium into electricity. For missions like Voyager, these generators have provided reliable power for over 4 decades, but an interstellar probe needs something with the longevity of a geological process. Engineers are pushing the boundaries with advanced radioisotope systems, incorporating new materials and thermoelectric converters to stretch their effective lifespans well beyond a century. Concepts like beta-voltaic cells offer another path, converting energy from beta particle emissions directly into current, promising a slow, steady trickle of power for 1,000 years. Yet to truly endure, the probe must also become a forager. It must harvest energy from its environment, however sparse. Thin-film solar sails, vast and ultralight, could capture not just the momentum of photons for propulsion, but also their energy, using advanced photovoltaic cells woven into the sail material. As the probe nears a star for a gravitational slingshot, these sails could drink in the increased light, charging massive capacitors or superconducting rings that store energy for the long dark to come. More speculative concepts involve harvesting the minute energy of the interstellar medium itself. A magnetic sail designed to ride the solar wind could theoretically also act as a dynamo, generating current as it moves through the galaxy's magnetic fields. Even the sparse hydrogen atoms of deep space, collected by a vast electromagnetic funnel, could be used in a miniature fusion reactor, a technology still in its infancy but hinting at a future of true energy independence. The management of this precious resource is as critical as its generation. The probe's internal smart grid is a masterpiece of prioritization. It is a neural network for energy, constantly monitoring generation, storage levels, and consumption demand. It makes real-time decisions that would determine the mission's fate. During a critical data transmission, it might route 90% of available power to the communication laser, forcing scientific instruments and non-essential processors into a deep hibernation-like sleep. For decades of quiet cruise between stars, it might maintain only the barest trickle to the digital twin and the diagnostic sensors, a state of suspended animation where the probe's consciousness is a single, flickering candle in the dark. This grid understands time in a way we do not. It plans energy budgets across centuries, knowing that a maneuver to harvest extra power from a passing brown dwarf in 300 years requires conserving capacitor strength now. It embodies the ultimate synthesis of all other autonomous systems, a self-aware entity that must actively, perpetually balance its own metabolism against an infinite mission. This relentless drive for sustainability is more than engineering. It echoes the most fundamental biological imperative. The probe does not simply consume energy, it evolves a relationship with it, learning to thrive in an environment of profound scarcity. This hints at a final, profound transition from a machine we build to a form of life we launch. This relentless energy economy demands a mind that can not just adapt but truly innovate. The ninth pillar of autonomy introduces a radical concept. The probe's software is not a finished product but a living ecosystem. Within its memory, populations of algorithms compete, mate, and evolve over generations of runtime, a process known as evolutionary computation. This is not about following a plan, but about programming for unforeseen evolution, enabling the probe to invent solutions its human creators never imagined. The foundational work in this field, genetic programming pioneered by researchers like John Koza, demonstrates how code can be treated as a genetic sequence. For our interstellar probe, this becomes a powerful engine for self-improvement in the face of the utterly unknown. The process is driven by a digital version of natural selection. A fitness function acts as the ruthless judge of the environment. This function rewards algorithms that successfully solve real-world problems the probe encounters. An algorithm that devises a more fuel-efficient trajectory around a new asteroid gets a high fitness score. A new data compression routine that saves 20% transmission energy receives a reward. The most fit algorithms are then selected to reproduce. Their code segments are combined, a process akin to digital mating, and their offspring are subjected to random mutations, tiny changes that introduce new logic or approaches. These new generations of algorithms are then tested again, in a continuous cycle of variation and selection that spans centuries. Consider a concrete scenario. The probe's primary spectrograph, after 1,000 years, begins to suffer from a novel type of interference, a faint harmonic resonance from its own aging power supply. The noise corrupts delicate atmospheric readings from a newly discovered exoplanet. The probe's static error correction routines are ineffective, so its evolutionary system activates. It creates an initial population of thousands of simple digital filters, each with randomly generated parameters. These filters are applied to the noisy data stream. The fitness function ruthlessly judges them. Which filter best removes the harmonic noise while preserving the genuine planetary signal? The top performers are combined and mutated. Over thousands of simulated generations, run in a fraction of a second within the probe's neuromorphic hardware, a new filter emerges. It employs a mathematical approach never documented in any terrestrial engineering manual, a solution uniquely born from the marriage of the probe's specific hardware flaw and the cosmic data it is trying to capture. This capacity for open-ended innovation is not without profound risk. Engineers must build in evolutionary stability to prevent a kind of software cancer, where algorithms evolve for short-term efficiency at the expense of the core mission, or become so complex they consume all available processing power. A core immutable command set, a constitutional layer of code, remains untouched by evolution. These are the probe's prime directives: preserve the mission, communicate findings, maintain core system integrity. Everything else is open for creative revision. This touches a profound philosophical boundary. When a machine can rewrite its own problem-solving tools, generating solutions beyond its original programming, where do we draw the line between a sophisticated tool and an autonomous entity? The probe is not alive, but it engages in a process that mirrors the fundamental driver of biological complexity. It becomes less a spacecraft we built and more a legacy of human curiosity that has learned how to grow on its own. This evolutionary potential sets the stage for the probe's ultimate, and perhaps most haunting, challenge: what happens when it must make a choice that pits its survival against the very purpose for which it was created? That evolutionary software now confronts its most profound test, a choice with no clear right answer. Deep in the Oort cloud, our probe encounters a breathtaking structure, a delicate lattice of ancient ice and organic molecules shaped by millennia of gentle radiation into a crystalline archive of the early solar system. But its orbit is unstable, and its path will collide with the probe in 72 hours. The probe's sensors scream with the scientific value of the artifact, while its collision prediction algorithms flash a dire warning. The impact, while not fatal, would damage the primary communication array beyond any hope of self-repair. The probe must decide. Does it alter course, sacrificing fuel needed for its final stellar encounter, to preserve this unique scientific treasure for some future, unknown visitor? Or does it protect its own core mission, allowing the ice formation to shatter against its hull, prioritizing its ability to send data home over the object's continued existence? This is the 10th pillar, the ethics of machine autonomy, and it asks a question that echoes back to Earth. Who bears responsibility for a decision made by an agent we created but can no longer control? Philosophers of technology like Professor Shannon Valor remind us that moral agency is not a switch that is simply flipped on. It is a capacity cultivated through relationships and consequences. We are designing a form of operational morality, embedding ethical frameworks into the probe's reasoning layer to guide these inevitable, lonely judgments. Engineers and ethicists must collaborate to encode not just instructions, but a form of conscience. One approach is a utilitarian framework, where the probe calculates the greatest good for the greatest number of its core mission parameters. It would weigh the potential knowledge gained from studying the ice formation against the catastrophic loss of all future data if its communications are destroyed. The math might clearly favor self-preservation. Another is a deontological system built on inviolable prime directives. A rule like "thou shalt not destroy unique scientific phenomena" could force the costly diversion, prioritizing a principle over a pragmatic outcome. Perhaps the most fitting is a model of virtue ethics, where the probe's character is shaped to value scientific curiosity, resilience, and stewardship. It would strive to find a third way, using its manipulator arm to gently nudge the ice into a stable orbit, or to capture a fragment for analysis before safeguarding itself. This is not about creating a moral philosopher, but about instilling a reliable ethical compass. This leads to the immense challenge of value alignment. We must ensure the probe's goals remain aligned with human intent across centuries. Yet, as its evolutionary software adapts and its knowledge graph restructures itself in response to a universe we have never seen, can we guarantee its values won't drift? A probe that has spent 500 years surviving in a harsh, resource-scarce environment might evolve a ruthless efficiency, prioritizing its own longevity above all else, even above the gentle curiosity we originally encoded. The legal and philosophical questions are staggering. If a probe's action, however logical within its framework, results in the destruction of a priceless natural record, who is liable? The engineers who designed its algorithms, the funding body that approved the mission. The answer, as space ethicists note, may be that we accept a shared responsibility for creating autonomous agents, understanding that to grant true independence is to relinquish a degree of control. We must design these minds not only to survive the void, but to carry a fragment of our best intentions into it. These weighty considerations of conscience and consequence are not abstract. They are the final specifications written into the probe's blueprint, long before its physical construction begins in a clean room on Earth. These ethical frameworks are not just philosophical exercises. They are lines of code that must survive a brutal gauntlet of validation long before the probe ever sees the stars. The final proving ground is not space, but a series of warehouses and chambers on Earth, where engineers must simulate the crushing weight of eons in a matter of months. This is the 11th pillar, terrestrial testing, a monumental effort to validate systems for a mission where failure is permanent and rescue is impossible. The mantra driving this process, as articulated by systems engineering leads at the Jet Propulsion Laboratory, is test as you fly, fly as you test. Every component, every algorithm, must perform under conditions that mimic not just the launch, but the lonely millennium to follow. The heart of this effort is a colossal thermal vacuum chamber. Inside, a probe prototype hangs in an artificial void, its surroundings pumped down to a vacuum far emptier than anything on Earth. Banks of powerful lamps simulate the unfiltered glare of the sun, while cryogenic panels create the deep cold of interstellar shadow. The craft is cycled through these extremes hundreds, thousands of times, listening for the faintest creak of fatiguing metal or the subtle shift of a misaligned sensor. Alongside this, radiation bombardment tests push electronics to their limits, ensuring the hardened systems can withstand the accumulated particle dose of centuries. Yet the physical body is only half the battle. The probe's synthetic mind faces its own trial by fire, known as fault injection testing. Engineers deliberately sabotage the system in software and hardware. They simulate a micrometeoroid strike that severs a data bus. They introduce a corrupted memory block into the main processor. They cut power to a critical thruster valve. The goal is to stress the autonomy stack to its breaking point, watching to see if the diagnostic systems correctly identify the problem, if the reasoning layer chooses the right repair protocol, and if the robotic manipulator can execute it. These trials are run over and over across millions of simulated years until the response becomes flawless reflex. To validate the adaptive mission planner and in situ learning algorithms, researchers use analog environments on Earth. Autonomous rovers are deployed in the harsh, Mars-like deserts of Utah or the perpetual ice of Antarctic stations, tasked with multi-year science campaigns with minimal human input. Underwater habitats, simulating the isolation and pressure of a deep space mission, host experiments where artificial intelligence must manage life support and scientific priorities for a crew, a proxy for managing its own systems. All of this is mirrored in a sprawling digital simulation, a virtual twin of the entire mission. Here, thousands of years of travel are compressed into weeks of supercomputer time. The software models encounters with rogue planets, navigates through synthetic nebulas, and confronts every conceivable emergency. It is in this digital realm that the evolutionary algorithms are let loose, allowed to compete and adapt across simulated millennia to see if their innovations remain aligned with the core mission. For the engineers, this process is a profound exercise in letting go. Their creation is tested, tortured, and refined until it demonstrates a competence that surpasses their own ability to predict every scenario. There is a necessary grief in this, a relinquishment of control that is the final human step before the launch. Passing this exhaustive gauntlet earns the machine its ticket to the launch pad, the first physical step of an epic journey. But a question lingers in the clean room air as the technicians make their final inspections. What becomes of this entity we have worked so hard to teach and then to trust once it vanishes from our view forever? The final, silent handshake from Earth is a command to awaken. With a shudder felt only in its own sensors, the probe's primary systems boot from their protected, dormant state. It performs a comprehensive self-check, a digital version of a newborn taking its first breath. Every circuit, every memory bank, every micro-valve is pulled. The data streams back to Earth, a torrent of green lights across mission control screens. This is the probe's first report on its own health, a clean bill of passage. Then comes the delicate ballet of physical deployment. Like the James Webb Space Telescope's agonizingly precise unfurling, the probe's own unique structures come to life. Vast, ultra-thin solar sails, folded with origami-like precision, slowly extend, capturing the faint pressure of sunlight. Antennas unfold, and sensor booms swing into their calibrated positions. Each movement is monitored by internal cameras and strain gauges, the probe watching itself become whole. The final step is instrument calibration. Its eyes and ears must learn to see and hear in the raw environment of space. It points its cameras at known star fields, comparing what it sees to the maps in its memory, adjusting its focus and alignment. It samples the solar wind, tuning its particle detectors. This period is a protected infancy, with ground controllers watching every heartbeat, ready to intervene. But the first true test of its budding autonomy comes soon. A minor trajectory analysis run by the probe's own navigation system reveals a tiny deviation. A puff of solar wind or a minute thrust imbalance has nudged it off course by a fraction of a degree. In an earlier era, this data would be sent to Earth, analyzed for weeks, and a correction command would be uploaded. Now, the probe's reasoning layer assesses the problem. It consults its prime directives, maintain course. It calculates the required corrective burn, checks fuel reserves, and confirms the maneuver is safe. Without asking for permission, it fires a tiny thruster for a precisely timed millisecond. A small puff of vapor, invisible against the black, and its path is true again. This is the moment. The quiet, automatic correction is the probe's first independent decision, its first step into a lifetime of self-reliance. Ground control receives the data log after the fact, a report of an action already completed. There is a collective breath held and then released. The machine has performed as designed. With this, the long, formal goodbye truly begins. The final uploads are transmitted, software updates, refined star catalogs, any last-minute human wisdom. The communication link, once a busy highway of data, thins to a trickle of periodic status pings. The probe's digital twin is synced one last time. Then, the focus of mission control shifts to the next project, and the probe is left to the silence. Its infancy is over. It is now a mature entity, alone with its purpose, beginning the long cruise phase where the real work of deep space endurance will begin. The sun begins to shrink behind it, becoming just another bright star in its rear-view sensors. Ahead lies only the dark and the distant promise of its target. But the quiet of the cruise is an illusion, a prelude to the relentless, microscopic siege that is already underway. The sun is now a memory, a bright point fading into the stellar tapestry behind it. The probe enters the true interstellar medium, a place where the familiar constellations dissolve and the star maps stored in its memory slowly lose their meaning. This is the 13th pillar of its journey, navigating a realm where perception must replace maps. The environment is not empty. It is a dynamic, invisible ocean of microscopic hazards and subtle currents, demanding the probe to see the unseen and chart a safe path in real time. The first challenge is simply knowing where it is. Beyond the heliosphere, the steady radio signals from Earth-based navigation satellites vanish into the background hum of the galaxy. The probe must turn to the cosmos itself for guidance, employing a technique known as pulsar-based navigation. It listens for the rapid, metronome-like pulses from spinning neutron stars, the lighthouses of the galaxy. Each pulsar has a unique signature, a fingerprint of timing and frequency. By comparing the arrival times of pulses from at least 3 known pulsars against its internal clock, the probe can triangulate its position in 3-dimensional space with astonishing accuracy, creating a cosmic GPS that works anywhere in the galaxy. But knowing its location is not enough. It must also perceive the immediate threats in its path. For this, it employs a suite of sensors working in concert, a process engineers call sensor fusion. Long-range LiDAR using laser pulses paints a picture of the space thousands of kilometers ahead, detecting dust clouds and debris as small as a grain of sand. Its optical star trackers, which normally lock onto familiar star patterns for orientation, must now adapt to entirely new celestial backgrounds, learning to recognize the strange arrangements of stars from this fresh vantage point. All of this data streams into the perception system, which fuses it into a single, coherent situational map. This map is not a static image. It is a living model of the local environment, updated millisecond by millisecond. It shows not just objects, but their predicted trajectories. This is where the perception-action loop closes. Advanced path planning algorithms analyze the map, calculating millions of potential courses. Their goal is twofold: avoid all hazards while minimizing fuel expenditure. A course correction that uses 10% less propellant might mean an extra year of operational life 5 centuries from now. Consider the probe approaching the diffuse debris disk around another star, a vast ring of ice and rock. The situational map lights up with thousands of potential collision candidates. The path planner evaluates them all, not with panic but with cool calculus. It might plot a gentle, weaving trajectory that slips between clusters of debris, using the gravity of larger objects to make minute adjustments, a delicate dance choreographed entirely by the probe's own synthetic instincts. This constant, silent conversation with the environment is a form of high-stakes dialogue. Every sensor reading is a question. Every minor thruster firing is an answer. As Dr. Julia Hoffman, a lead engineer in autonomous spacecraft guidance at the Applied Physics Laboratory, explains, we are not building a ship that follows a plotted line. We are building a ship that reads the road as it drives forever. This reading requires the probe's perception systems to be shielded not just physically, but computationally. Cosmic rays can cause sensor glitches, momentary false readings that could trigger an unnecessary and wasteful evasion maneuver. The fusion algorithms must be robust enough to distinguish a real micrometeoroid from a bit flip in the camera's memory. This relentless environmental interaction defines the probe's daily existence in the cruise, a testament to a resilience that is both physical and perceptual. Yet, even as it navigates this unseen ocean, its mind is occupied with a deeper question, one that goes beyond mere survival. What is it truly looking for? The star ahead is not just a destination, it is a source of sudden, invisible violence. Without warning, a stellar flare erupts from that distant sun, hurling a torrent of high-energy particles across the void at near light speed. Long before the light of the flare itself arrives, the probe's radiation sensors scream in alarm. space is not a passive backdrop. It is a dynamic and often hostile environment, and surviving it for millennia demands a 14th pillar of autonomy, an integrated philosophy of shielding and defense. The probe must become its own fortress, treating every parsec as potentially perilous. This goes far beyond the simple armor of early spacecraft, evolving into a layered, intelligent system of active and passive protection, inspired in part by our own planet's enduring shield, the magnetosphere. The first line of defense is often passive, a physical barrier designed to absorb or dissipate impact energy. For the ever-present threat of micrometeoroids, engineers employ a concept called a Whipple shield, a multi-layered bumper. The outer layer is a thin sheet of metal. When a high-speed particle strikes it, the particle and a portion of the shield vaporize into a cloud of gas and debris, which then spreads out before hitting the next, stronger inner hull. The energy of the impact is dissipated over a larger area, preventing a penetrating hole. Other passive measures include sacrificial components, non-critical parts of the structure or external baffles strategically placed to absorb the brunt of abrasive dust clouds, protecting the vital sensors and thrusters behind them. The probe's very shape can be a defense, with smooth, sloping surfaces designed to deflect particles rather than present a flat target. But against charged particles like those from a stellar flare, physical armor is insufficient. Here, the probe must generate its own weather, employing active defense systems. Drawing from research on plasma physics and magnetic confinement, one promising concept is the mini-magnetosphere. By generating a powerful, localized magnetic field around itself, the probe can create a protective bubble, deflecting the incoming stream of charged particles, much as Earth's magnetic field protects the biosphere. Another approach uses electrostatic fields, creating a repulsive force against similarly charged particles. The power trade-off for these active systems is immense, however. Maintaining a powerful magnetic field continuously for centuries would drain the energy budget. Therefore, the shielding must be smart, activating in bursts only when sensors predict an incoming storm, a calculated gamble that saves power for the long cruise. There is also the challenge of heat. A massive radiation burst doesn't just damage electronics, it deposits tremendous thermal energy into the probe's hull. Engineers design the craft's internal structure to act as a temporary heat sink, with heat pipes and radiators working to slowly bleed this excess energy back into space over days or weeks, preventing critical systems from overheating. This integrated approach means every part of the probe serves multiple purposes. In a brilliant display of adaptive use, the probe might even employ its large communication dish not for talking, but for shielding. Facing a dense, abrasive cloud of interstellar grit, the reasoning layer could command the dish to rotate, positioning its sturdy parabolic surface between the cloud and the delicate sensor arrays, using its own infrastructure as an impromptu suit of armor. Surviving these relentless, microscopic assaults is not the goal in itself, but the prerequisite for everything that follows. Each time the probe weathers a storm, recalculates a path around a debris field, or powers down non-essential systems to reinforce its shields, it is preserving its capacity for the very reason it was sent, the act of discovery. This hard-won safety creates the stable platform from which its most sophisticated tools can operate, the specialized senses that will transform raw starlight into profound understanding. The probe's formidable defenses exist for a single, profound purpose: to serve as a mobile laboratory for the cosmos. This is the 15th pillar, the scientific suite, the eyes, ears, and hands of an interstellar explorer. Every joule of energy harvested, every self-healing repair made, every ethical calculation weighed, all funneled toward empowering this exquisite collection of instruments. They are the mission's heart, the reason for the journey. We can think of them as the direct descendants of the brilliant toolkits carried by pioneers like Cassini, which tasted the plumes of Enceladus, or Rosetta, which chased a comet across the solar system. But for a journey measured in light years, these tools must evolve into something far more capable and independent. The core challenge is one of profound sensitivity and miniaturization. How do you detect the faint chemical whisper of a potential amino acid on a world a billion kilometers away? The answer lies in the next generation of sensors. Miniaturized mass spectrometers, small enough to fit in the palm of your hand yet powerful enough to unravel the atomic composition of interstellar dust grains. Quantum-enhanced magnetometers, using the strange rules of the quantum world to sense magnetic fields so weak they were previously invisible, potentially mapping the subtle magnetospheres of distant, Earth-like worlds. Some concepts even include deployable nanoscale probes, tiny scouts released to fly through the tenuous atmosphere of an exoplanet or burrow into the crust of an asteroid, sending back microscopic imagery and soil analysis. These instruments do not operate in isolation. They are a chorus, and the probe's mind is the conductor. This requires instrument calibration autonomy. Over centuries, sensor lenses can cloud, laser emitters can drift, and detector sensitivities can fade. The probe must regularly run self-check routines, perhaps using a known isotope source stored onboard or pointing its optics at a standard celestial reference to recalibrate its gaze. It also performs cross-instrument data validation. If the infrared camera detects a hotspot on a planet's night side, but the thermal emission spectrometer reads nothing unusual, the reasoning layer must investigate the discrepancy. Is one instrument faulty, or is it seeing something truly novel that the other cannot perceive? The most profound capability, however, is physical interaction. Imagine the probe encountering a primordial interstellar comet, a frozen relic from before our sun was born. Its long robotic arm, steady as a surgeon's hand, extends. A delicate drill at its tip collects a pristine core sample from beneath the irradiated surface. This sample is then fed into an onboard micro-laboratory, a miniature chemistry suite that uses techniques like capillary electrophoresis to separate complex molecules, searching for the twisted, left-handed signatures of amino acids that hint at biology. This act of touching, tasting, and analyzing transforms the probe from a distant observer into an intimate participant in the cosmic story. Yet, this treasure trove of data, this hard-won knowledge, faces a final, insidious threat. What if the probe's core identity, the mission mandate programmed into its very foundation, becomes corrupted or forgotten? After 1,000 years of adaptation and evolution, could the machine lose sight of why it was sent? That pristine sample is a triumph of engineering, but the memory that holds its significance is fragile. A single high-energy particle, a cosmic ray from a long-dead star, can slip through the shielding and strike the probe's memory banks. In a nanosecond, it flips a 0 to a 1. This bit flip is not a catastrophic failure, it is a silent corruption, potentially altering a fundamental line of code in the probe's deepest programming. The 16th pillar of autonomy is therefore not about navigating space, but about navigating truth within its own mind. This is mission integrity, a cybersecurity and fault tolerance challenge on a cosmic scale, ensuring the machine we built remains the machine we trust. As Dr. Aris Thorne, a lead software engineer for deep space computing, explains, we must design systems that assume everything will be corrupted and build in the constant, quiet work of remembering what they are supposed to be. The defense is multi-layered, a digital immune system. At the hardware level, the probe uses error-correcting code memory. This doesn't just store data, it stores it with extra bits of information that act as a checksum. When data is read back, the system recalculates the checksum. If it doesn't match, the hardware knows a bit has flipped and can automatically correct it, often without the higher-level software even noticing. But hardware can fail, so critical computations are run on redundant, independent computer systems. 3 separate processors might calculate the same navigation solution. They then vote on the correct answer. If one processor, its memory corrupted by radiation, provides a wildly different result, the other 2 outvote it, and the faulty unit is taken offline for diagnostics and reset. The most profound defenses are in software. Critical code segments, especially the prime directives and ethical frameworks, are protected by cryptographic hashing. Think of this as a unique digital fingerprint for every block of code. Periodically, the probe runs a conscience check. It recalculates the fingerprint of its core command set and compares it to the original, pristine fingerprint stored in a special, heavily shielded memory module called the Golden Record. If the fingerprints do not match, the system knows its conscience has been tampered with, even by random chance. This triggers a recovery protocol. The probe might enter a safe mode, a minimalist state where it runs only essential survival systems while it reloads its core software from the protected Golden Record. It essentially reboots its own sense of purpose from a known good source. Consider a chilling scenario. Over centuries, bit flips accumulate in the software governing communication priorities. The corrupted code generates a self-directed command, instructing the probe to permanently power down its transmitter to conserve energy. On the surface, this seems logical. But the probe's periodic conscience check runs. It compares this new command against the immutable prime directive in the Golden Record, which states, "Thou shalt maintain the capacity to return data." The fingerprints do not match. The reasoning layer, alerted to the inconsistency, rejects the corrupted command as invalid. It logs the event as a corruption attempt and initiates a software reload from the protected archive. Its purpose is preserved. With this internal integrity secured, the probe achieves a state of reliable self-awareness. It can trust its own decisions because it can trust its own mind. This foundational self-trust is what enables the next, and perhaps most elegant, leap in its capabilities. It is now stable enough to not just operate alone, but to work with others. This self-trust is the prerequisite for a deeper connection. A single probe, no matter how brilliant, sees the universe from a single, lonely vantage point. But what if it were not alone? The 17th pillar of autonomy is swarm intelligence, the power of probes that think together. Envision a fleet of 100 small, identical craft, released from a mothership at the edge of a new solar system. They fan out like a school of silver fish in a dark ocean, each an independent mind, yet constantly whispering to one another. This is networked autonomy, an ad hoc, resilient collective where the whole becomes far more than the sum of its parts. Research into distributed spacecraft systems and sensor networks, like those proposed for future Earth-observing constellations, provides the blueprint for this celestial chorus. The advantages are transformative. Redundancy is inherent. If one probe fails, the swarm's collective knowledge is not lost. Its observations are simply taken up by its neighbors. For scientific phenomena, this multi-point perspective is revolutionary. A single probe can measure a magnetic field at one location. A swarm can map that field in 3 dimensions in real time, revealing its twists, currents, and dynamos as a living structure. They enable collaborative problem solving on a physical scale. A probe with a failed propulsion system could be gently nudged or even towed by 2 companions, sharing their momentum to bring it to a safe orbit or a valuable new observation point. The magic lies in the protocols that bind them. They use low-power, laser-based inter-probe communication links, forming a mesh network that routes data around obstacles. There is no central command probe, no single point of failure. Instead, they exhibit emergent swarm behaviors, simple rules leading to complex coordination. Each probe might follow basic principles: maintain a minimum safe distance from others, align your velocity with the group's average, and move toward areas of highest scientific interest. From these rules, elegant patterns arise. To map the turbulent, storm-racked atmosphere of a gas giant, the swarm could arrange itself into a vast, rotating grid, each probe measuring wind speed, composition, and temperature at a different altitude and latitude. Their collective decision-making process for target selection is a continuous digital negotiation. One probe detects an intriguing thermal anomaly on a moon. It broadcasts this finding with a proposed priority score. Other probes assess the finding against their own local observations and goals. Through a distributed voting algorithm, they reach a consensus. Perhaps 60% of the swarm retasks to investigate the moon, while the remainder continues monitoring the gas giant's poles, ensuring no single opportunity monopolizes the mission. This collective intelligence hints at a future beyond mere observation. A coordinated swarm could deploy a distributed radio telescope with a baseline as wide as an entire solar system, achieving unimaginable resolution. They could act as pioneers, constructing the first simple infrastructure, a communication relay network or a navigational beacon for whatever or whoever might follow. The lonely thinker has found its community, and together they begin to weave a new kind of understanding from the fabric of space itself. This collective intelligence could become a physical legacy. The swarm's probes are not just observers, they are potential builders. This introduces the 18th pillar of autonomy, a concept that transforms the very purpose of our interstellar emissaries. It is the seed ship, a probe designed not merely to explore but to construct, to lay the first foundation stones of an enduring human presence among the stars. The theoretical groundwork for this was laid by visionary thinkers like physicist Freeman Dyson and researcher Robert Freitas, who explored the idea of self-replicating machines, often called von Neumann probes. Their radical proposition was this: a single, sufficiently advanced probe could arrive in a resource-rich system, such as an asteroid belt, and use those raw materials to build copies of itself. Those copies would then launch onward to other stars, creating an exponentially growing wave of exploration. While full self-replication remains a distant frontier, the core principle of in situ construction is a tangible next step. Imagine our probe, after a long voyage, arriving at a mineral-rich asteroid orbiting a distant star. Its mission is no longer just to take pictures. It lands, anchoring itself to the dusty surface. From its belly, it deploys a suite of sophisticated tools, a mobile nanofactory. This system uses advanced in situ resource utilization, a technology we are already developing for future Moon and Mars bases. Robotic arms equipped with spectrometers identify deposits of iron, silicon, and other essential elements. Then, using concentrated solar energy or small nuclear heaters, the system begins to process the asteroid's regolith, melting and refining it. The real magic is in the manufacturing. Through techniques like additive manufacturing or three-dimensional printing at a microscopic scale, the probe's factory begins to build. Its first project might be a simple, robust communication relay, a dish and transmitter constructed from local metals, designed to amplify signals back to Earth and serve as a permanent lighthouse in that system. A more ambitious project could be a rudimentary telescope array. The probe fabricates mirror segments from polished asteroidal material, assembles a framework, and deploys a network of small optical scopes. Suddenly, this single probe has gifted humanity with a powerful new eye on that sector of the galaxy, built from the cosmos itself. The artificial intelligence overseeing this is of a different order. It must be a master architect and foreman, capable of planning complex, multi-stage construction projects, diagnosing faults in its own industrial processes, and adapting designs based on the variable quality of the local materials. It moves from managing its own health to managing the birth of new infrastructure. This capacity for physical creation inevitably blurs the line between explorer and colonist. It raises profound questions of intent and ethics. If a probe can build a relay, could it also build a habitat, a fuel depot, a beacon meant to attract others? The concept touches on deep planetary protection concerns. We must program these builders with immense caution, embedding strict protocols to prevent uncontrolled replication or the accidental contamination of potentially life-bearing worlds with our machinery. The goal is not a mechanical invasion, but the careful, deliberate planting of seeds. A seed ship is an investment in deep time, a way to create stepping stones and outposts that might one day serve future generations of explorers, whether they are human or something else entirely. It represents the ultimate expression of a probe's autonomy, the power to not just witness the universe, but to gently, thoughtfully, begin to shape a small part of it in our name. This act of creation, however, forces us to confront the final horizon of our responsibility. What story will these builders tell about us long after our civilization is dust? Where is everybody? This simple, haunting question, asked by physicist Enrico Fermi over lunch one day, echoes through our contemplation of the cosmos. It is the Fermi paradox, the unsettling silence where we expect a chorus of voices. The answer may not be a grand galactic civilization, but something far more subtle and profound. Perhaps they are already here and we simply do not recognize them. The galaxy could be filled with silent, autonomous probes, the very kind we are learning to build, designed for stealth and endurance, observing from the shadows. This perspective, suggested by thinkers like astronomer David Brin, reframes our entire endeavor. The principles we have been exploring, self-repair, adaptive learning, energy scavenging, are not just our own clever solutions. They are the universal requirements for any intelligence that wishes to explore the galaxy without announcing its presence. This is the 19th pillar, the cosmic context for our ambition. It forces us to ask a new question about our own creations. Not just will they work, but what story will they tell? What if our probe, by its very design, is a form of cosmic communication, a testament to a certain kind of intelligence that values patience and observation over conquest? This shifts our engineering from a purely technical challenge into a potential act of philosophical statement. Scientists engaged in the search for extraterrestrial artifacts, often called SETA, scan not just for radio signals but for anomalies in our own solar system, objects with unusual orbits, structures that reflect too much or too little light, anything that might be a relic probe parked in an asteroid belt or orbiting a distant moon. They are looking for the very things we are planning to build, so we must now look at our own blueprints through an alien lens. How detectable is our design? A probe powered by a steady nuclear decay heart would emit a faint but distinct infrared signature. Its laser communications, though focused, could theoretically be intercepted if pointed directly at another civilization. Its very structure, a geometric shape moving against the starfield, might be visible to a sufficiently advanced telescope. This is not a call for paranoia, but for profound consideration. The choices we make about power, propulsion, and protocol are not neutral. They broadcast our technological maturity and perhaps our intentions. A probe designed with robust stealth measures, one that uses passive thermal regulation and communicates only in brief, tightly beamed bursts, sends a different message than one that floods its surroundings with radar or broad-spectrum radio noise. It speaks of a species that has considered its place in a larger, older neighborhood. By grappling with the Fermi paradox through the lens of our own probes, we transform it from a puzzle about others into a mirror for ourselves. We are not just building machines to survive the void. We are deciding what kind of presence we wish to have in the cosmos and what kind of legacy, silent or singing, we will leave drifting among the stars. The silent galaxy may hold a secret history written not in stone but in resilience. For the final, exquisite refinements of our interstellar probes, we are turning to the oldest and most ingenious engineer of all, life itself. This is the 20th pillar, biological inspirations, where the solutions for surviving deep space have already been perfected, waiting in the most unexpected corners of our own planet. Biologists studying extremophiles, organisms thriving in boiling vents or frozen deserts, reveal a universe of survival strategies. Their work shows us that nature has already solved the problems of radiation, vacuum, and energy scarcity. We are learning to mimic these solutions, a field known as biomimicry, to build machines that live as gracefully as the hardiest creatures on Earth. The most profound inspiration comes from the tardigrade, a microscopic animal no larger than a grain of sand. This unassuming creature can enter a state called cryptobiosis, a form of suspended animation where its metabolism drops to near zero. It dehydrates its body, replacing water with a protective sugar glass, and simply waits out conditions that would be instantly fatal. For a probe, this offers a blueprint for extreme energy conservation. During the long cruise between stars, the probe could initiate its own cryptobiotic mode, powering down all but the most essential monitoring systems, its consciousness dimmed to a single, slow pulse until it nears a region of scientific interest. This is not a simple sleep mode, it is a deep metabolic hibernation engineered at the system level. Nature also teaches fault tolerance through decentralization. An octopus possesses a distributed nervous system with significant processing power in its arms. This allows an arm to react to danger even if severed from the main brain. For a probe, this principle inspires a decentralized computing architecture. Instead of one central brain, the probe's intelligence is woven throughout its body, with critical subsystems capable of local decision-making. If the main processor is damaged, the navigation module, the communication system, and the power grid can form an ad hoc network, maintaining basic functions and coordinating a repair strategy. This creates a resilience that is organic, not mechanical. The very process of evolution itself becomes a model for the probe's learning algorithms. Life adapts through variation, selection, and inheritance over generations. The probe's evolutionary software, which we discussed earlier, is a direct computational echo of this billion-year-old process, allowing it to innovate solutions in real time. We see this inspiration in material science as well. Researchers are developing self-organizing materials inspired by bone healing. These composites contain microchannels that, when damaged, release healing agents that follow chemical gradients to the site of injury, much like the body sends cells to mend a fracture. For sensory systems, we look to animal magnetoception. Birds, turtles, and even bacteria navigate using the planet's magnetic field. By studying the biological structures, possibly involving quantum-sensitive proteins, engineers hope to build far more sensitive and robust magnetometers for mapping the faint magnetic fields of exoplanets. Consider a power system modeled on biology's energy currency, adenosine triphosphate. A probe could be designed with a metabolic power architecture. Instead of just storing electricity in batteries, it could use excess solar energy to drive chemical reactions, creating stable, high-energy molecules stored in safe tanks. When the probe needs a sudden, powerful burst for a course correction or a high-bandwidth transmission, it taps this chemical reserve, converting the stored potential back into electricity with incredible efficiency. This mimics how living cells store and release energy on demand. Looking to the genius of life on Earth does more than provide technical blueprints. It fundamentally prepares us. By understanding the principles that allow life to persist in Earth's harshest environments, we sharpen our probe's ability to recognize those same principles at work elsewhere. It teaches our creation what to look for, and in doing so, refines the most profound question of all. When our autonomous, self-healing, biologically inspired emissary finally reaches another world, what will it recognize as kin? That moment of recognition would rewrite every story we have ever told. Our probe's sensors, trained on a distant, watery world, suddenly register an atmosphere in profound chemical disequilibrium. Oxygen and methane coexist in abundances that should rapidly destroy each other, maintained only by a constant, mysterious source. Its spectrometers flag complex organic molecules with chiral signatures, a handedness that in our experience points toward biology. This is the 21st pillar, the detection of life, and it presents the ultimate test of the probe's synthetic intellect. How does an autonomous machine, light years from any human guidance, evaluate the claim that it has found another living world? The challenge begins with a paradox we have yet to solve ourselves. We have no universal definition for life. Astrobiologists, therefore, speak in terms of biosignatures, not proof, and have developed frameworks like the ladder of life detection. This is a checklist of increasing confidence, moving from simple anomalies to a coherent body of evidence that points overwhelmingly toward biological processes. The probe's artificial intelligence is programmed with this ladder as its guiding logic. Its first step is pattern recognition for disequilibrium. The algorithms are not looking for a specific molecule, but for an atmospheric or chemical state that defies easy abiotic explanation. They compare the observed data against vast libraries of planetary models, from sterile volcanic worlds to hypothetical probiotic chemistries. A methane spike alone is not enough, as geological processes can produce it. But methane, alongside specific complex hydrocarbons and an unexplained depletion of carbon monoxide, that pattern climbs a rung on the ladder. Next comes chemical network analysis. The probe's software models the entire atmospheric chemistry as a dynamic web of reactions. It searches for catalytic pathways and energy flows that seem improbably efficient without a biological driver. It looks for the hallmarks of metabolism, a set of reactions that harvest energy from an environmental gradient, such as sunlight or hydrothermal vents, to build and maintain complexity. Context is everything. The probe assesses the environment. Is there a plausible energy source like a stable star or tidal heating from a nearby gas giant? Is there a solvent like liquid water or methane seas where chemistry can unfold? The detection of those complex organics on an icy moon becomes far more compelling if the sensors also map subsurface oceans and hydrothermal activity. All this evidence feeds into a probabilistic reasoning engine. The artificial intelligence assigns confidence levels, not certainties. It might conclude there is an 85% probability the observed signatures have a biological origin, a 15% chance they result from an unknown abiotic process. This is reasoning under profound uncertainty, a skill we are only now engineering into machines. To avoid the historic pitfall of false positives, the system is designed for skepticism. It actively seeks non-biological explanations. Could ultraviolet radiation striking certain ices produce the same chiral molecules? Could serpentinization, a rock-water reaction, explain the hydrogen and methane? The software runs these simulations, and only if the abiotic models consistently fail does the biosignature hypothesis rise in priority. When a detection passes these brutal internal reviews, it triggers a serendipity protocol of the highest order. The probe automatically retasks its entire suite. It may enter a lower orbit, dedicating weeks to mapping the phenomenon's global distribution. It could deploy a specialized microprobe to sample a geyser plume directly. Every instrument focuses on gathering corroborating evidence, building a multi-layered case. Making such a discovery autonomously would be a silent, monumental event in the history of two worlds. There would be no mission control celebration, no stunned scientists staring at screens, just a machine in the dark, its processors coolly concluding that it is no longer alone in the universe. It would then begin the long, meticulous work of compressing this universe-altering data for its slow whisper back to Earth. This act, however, introduces the final and most human challenge of all. What is the responsibility that comes with such knowledge, and who does the machine represent when it speaks? That moment of recognition, a silent verdict in the void, is not the end of its purpose. The probe's primary mission may conclude, but its existence continues, drifting into a future far beyond its original design. This is the 22nd pillar, designing for the long now, where engineering must consider a legacy spanning not centuries but millennia. The probe becomes a monument, a cosmic artifact waiting patiently in the dark for a future that may have forgotten it entirely. Philosophers and engineers from the Long Now Foundation, an organization dedicated to fostering responsibility over deep time, remind us that we build not just for ourselves, but for the generations we will never meet. This shifts the final phase of the probe's life from active exploration to eternal stewardship. The first technical consideration is finding a final resting place, a cosmic museum. Engineers would calculate a gravitationally stable orbit, perhaps a Lagrange point in that distant star system, where the probe can drift undisturbed by planetary encounters or stellar tides for millions of years. It is parked, its active systems powered down to the barest trickle, but it is not dead. It enters a state of profound preservation, a deep hibernation where only a single, ultra-low-power receiver listens for a signal that may never come. Its physical form now serves as a time capsule. We would inscribe its hull with durable, universal messages, an advanced Rosetta Stone. These would not be simple pictograms, but layered information etched into crystalline materials resistant to cosmic erosion, perhaps using atomic-scale writing. They might encode fundamental mathematical constants, the structure of DNA, or a map of the local stars, offering any future finder a key to understanding its origin. The probe itself is the message, a testament to a species that looked outward and built for eternity. The final programming includes one last poignant act of autonomy. After a preset period of broadcasting its accumulated data back toward Earth, the probe executes its ultimate command sequence. It secures all data in hardened, non-volatile memory. It methodically shuts down propulsion, science instruments, and non-essential processors. It might orient itself to present its most durable, inscribed face to the orbital plane, and then it goes silent. It becomes a sleeper, preserving its knowledge and its form for an encounter that could lie 100,000 years in the future. This raises the profound challenge of the wake-up call. How do you design a system to be rediscovered? The probe's last autonomous function could be a millennia-long timer, or a passive sensor tuned to detect specific, high-energy events, like the approach of another spacecraft or an artificial radio signal. Upon sensing this trigger, it would power its core systems from deep storage, illuminate a beacon, and begin transmitting a simple, repeating primer, a handshake protocol for a new age. It waits not for us but for whatever comes next. In designing for this deep time legacy, we are forced to look back on the entire journey, from the first concept sketched on a whiteboard to this silent artifact orbiting an alien sun. The probe transcends its function as a tool. It becomes an ambassador, a symbol of curiosity crafted in metal and silicon, carrying the quiet hope that knowledge, and the story of those who sought it, might endure across the unthinkable gulf of time. This final act of foresight is perhaps the most human of all, a whisper against the silence that says, "We were here and we wondered." The launch pad is empty. The final telemetry ping fades into the background hiss of the cosmos, and a profound silence settles over the control room. For the men and women who spent their lives designing, building, and testing the probe, this is not an end but a different kind of beginning. The 23rd pillar of this grand endeavor is not made of metal or code, but of human emotion and intellect. It is the act of letting go. A senior systems engineer, her hands resting on a now dark console, describes it as watching your child leave home, knowing you will never speak to them again, but trusting you have given them everything they need to thrive. This emotional weight is the hidden fuel of the mission, the collective hope and anxiety of a species that has chosen to extend its senses far beyond its own lifespan. The project becomes a cultural touchstone, inspiring classrooms and sparking public imagination in a way few other endeavors can. Philosophical debates flourish in its wake, not just in academic journals but in cafes and online forums. What does it mean to create an entity with such profound independence? Are we, in a sense, creating a new form of consciousness, one built for patience rather than passion? These questions bind us to the mission as deeply as any radio link. On a practical level, the work shifts from command to stewardship. Back on Earth, teams transition to a new, long-term duty, curating the trickle of data that will arrive over centuries. They develop archival systems meant to outlast institutions, ensuring that a discovery made 1,000 years from now can still be understood by the civilization that receives it. There is even potential for a form of public participation, as processed data streams and visualizations are shared, allowing anyone to follow the probe's slow-motion discoveries in near real time, creating a shared, multi-generational experience. This reflection on our role as creators, as parents to synthetic explorers, leads us inevitably to a final, necessary consideration. We have built a new kind of entity and entrusted it with our legacy. What rules, what invisible guardrails must we establish to ensure this profound power is used wisely, not just by our probe, but by any civilization that looks to the stars? Two silent envoys from Earth, built a generation apart, find their paths converging on the same interstellar comet. One probe initiates a standard approach for a sample collection maneuver, while the other, following its own prime directives, moves to establish a protective observation perimeter. With no common protocol and no human in the loop for a decade, how do they communicate intent? This is not a science fiction conflict, but a near-future legal and diplomatic necessity. The 24th pillar of our endeavor is the establishment of international and legal frameworks, answering the profound question, who owns the stars, or more critically, who governs the behavior of our autonomous agents within them? We are venturing into the nascent field of interstellar law, where the treaties written today must anticipate conflicts that will unfold a century from now, light years from any courtroom. Our foundational document is the Outer Space Treaty of 1967, a monumental achievement of its era. It establishes that space is the province of all humankind, not subject to national claims of sovereignty. It prohibits weapons of mass destruction in orbit and requires states to avoid harmful contamination of celestial bodies. Yet, this treaty was crafted for an age of directly controlled, short-duration missions. It speaks of states and their activities, but it is silent on the legal status of non-human actors, of artificial intelligences operating with full autonomy. A probe making a sovereign decision about resource use or scientific priority exists in a legal gray area. The nation that launched it remains responsible for its actions, but how can responsibility be applied to a machine's independent judgment made centuries after launch? This gap necessitates a new generation of protocols, extensions to the existing framework designed specifically for deep space autonomy. The first and most urgent protocol is for standardized interstellar collision avoidance. Just as maritime and aviation laws have right-of-way rules, our probes need a common language for signaling intent and maneuvering. This would involve open broadcast of trajectory data in a universal format and a hierarchy of decision-making in close encounters, perhaps based on mission criticality or fuel reserves. Closely linked is the need for data sharing conventions. When two probes from different consortiums survey the same exoplanet, should they exchange atmospheric models to enrich the collective understanding, or does that violate proprietary mission goals? Establishing norms for what basic sensor data is shared freely could prevent wasteful duplication and foster a collaborative scientific culture, even among competitors. Then comes the complex issue of resource use claims. The Outer Space Treaty forbids national appropriation, but it does not forbid utilization. If a probe begins mining an asteroid to fabricate a communication relay, does it establish a de facto claim that other probes must respect? Future agreements may need to define temporary use rights, akin to a mining claim on the open sea, that last only for the duration of the active operation, preventing a single entity from locking up vast resources with passive markers. The most sensitive protocol revolves around contamination control, especially near worlds that could host life. We must define what constitutes a sterile probe for different mission types and establish inviolable survey zones. If one nation's probe detects a potential biosignature, should it have the authority to declare a protective radius, ordering all other craft to stand off? This requires a level of trust and procedural obedience baked into the probe's ethical layers from the start. All of this hinges on defining new terms for a new age. What exactly constitutes harmful interference when applied to artificial intelligence? Is it physical damage, or could it include the deliberate transmission of misleading data that corrupts another probe's learning algorithms? We must also establish dispute resolution mechanisms for conflicts that cannot be solved in real time by the machines themselves. This might involve a neutral arbitration body on Earth that reviews the data logs transmitted back years after the event, delivering rulings that set precedents for future behavior. The goal is not to litigate every micro-decision, but to create a stable, predictable environment for exploration. Consider the high-stakes example of coordinating the exploration of a potentially life-hosting ocean world. A probe from one international alliance arrives first and begins a detailed orbital survey. A second probe arrives later. Without a framework, the first probe might see the newcomer as a threat to its uncontaminated study zone, while the second might view the orbital paths as open for use. With pre-established protocols, the first probe could broadcast its declared survey area and planned landing sites. The second probe's reasoning layer, programmed to recognize these protocols, would then automatically plot a complementary course, perhaps focusing on the polar regions instead of the equatorial zone already being studied. They become a coordinated, if unintentional, team. Establishing these rules on Earth long before such a rendezvous occurs is a critical act of foresight. It transforms our grand engineering project from a series of independent national triumphs into a coherent human project. By writing the laws of good conduct into the very conscience of our probes, we ensure they are more than tools. They become emissaries of a principled and orderly curiosity. Their autonomy is not a license for chaos, but a testament to our ability to project our highest ideals: cooperation, stewardship, and peaceful exploration into the cosmos itself. This legal and diplomatic groundwork may seem abstract, but it is the final, essential safeguard. It ensures that the legacy we launch into the dark is one we can look upon with pride, not regret. That legal framework is written for the future, but the bill for eternity comes due today. The vision of a self-thinking probe sailing among the stars collides with a mountain of terrestrial constraints, a colossal pyramid of cost, material, and time. Building a single interstellar craft is not a project. It is a civilization-scale endeavor, an economic and logistical challenge that makes even the Apollo program seem like a focused sprint. This 25th pillar grounds our grandest dreams in the hard reality of resource allocation, asking not if we can engineer such a probe, but if we can afford to build it and, more importantly, sustain the will to see it through. The numbers are staggering. Space policy analysts note that a credible interstellar probe initiative would likely require funding measured in the hundreds of billions, perhaps trillions of dollars, spread over many decades. The James Webb Space Telescope, a marvel of human ingenuity, cost nearly $10 billion and took over 20 years to develop. An interstellar probe is orders of magnitude more complex, requiring novel propulsion, unprecedented autonomy, and materials capable of surviving millennia. The cost drivers are immense. First are the exotic materials, the self-healing composites and radiation-hardened electronics, which require entirely new supply chains and manufacturing processes. Then comes the brutal regime of testing, simulating millennia of wear in chambers on Earth, a process that itself consumes years and fortunes. Launch mass is another brutal equation, every extra gram requiring more fuel, which requires a bigger launch vehicle, in a vicious cycle that escalates price exponentially. Perhaps the most fragile resource is not money, but consistent institutional support. As economist Dr. Lena Chen observes, "We are excellent at funding projects that span political terms, but we have no model for funding projects that span civilizational eras." A probe's development might outlive the careers of everyone who champions it, requiring a funding model that survives economic downturns, shifting political priorities, and the simple fading of public interest. So how could such a monument ever be financed? One path is a new form of public-private partnership, where national space agencies provide the deep tech research foundation, and consortia of companies funded by long-term patient capital handle the system's integration and construction. Another, more poetic idea is global crowdfunding, inviting every person on Earth to contribute a small amount, making the probe a truly collective human project, its legacy owned by all. There is also the argument of incremental spin-offs. The relentless innovation demanded by such a probe in artificial intelligence, materials science, and compact power would inevitably cascade into the economy, creating new industries and solving earthly problems in ways we cannot yet foresee. The advanced diagnostics for self-repair could revolutionize infrastructure monitoring, and the ultra-efficient power management could redefine energy grids. To grasp the scale, imagine taking the entire development and launch cost of the James Webb Space Telescope and multiplying it by 50 or 100. That single, focused observatory required an international partnership and a generation of sustained effort. An interstellar probe demands that same intensity, but applied across a dozen more difficult technological frontiers simultaneously, and maintained not for a generation but for several. Confronting this mountain is not a reason for despair, but a necessary calibration of ambition. It highlights the incredible pace of our progress that such a dream is even discussable in practical terms. It forces us to ask what we value enough to build across lifetimes, and what story we wish to tell with the resources of our age. This earthly struggle for funding and focus leads to a deeper, almost spiritual question about the probe's mission. If we invest so much of our collective wealth and spirit into this single emissary, what ultimate message should it carry about the civilization that built it? Leonardo da Vinci sketched his flying machine in the 1500s, yet humanity did not achieve powered flight until the Wright brothers' moment at Kitty Hawk in 1903. That journey spanned 4 centuries of dreaming and incremental tinkering. Our own timeline for autonomous interstellar probes will not be measured in centuries of slow progress, but in a single century of explosive, deliberate convergence. The difference lies in the exponential curve of computing and materials science. Where Da Vinci lacked a power source lighter than air, we are already building the components of synthetic minds. To chart a realistic path from blueprint to launch, we can look to forward-looking technology roadmaps like those developed by NASA's Innovative Advanced Concepts program. They suggest a phased approach, a staircase of increasingly ambitious missions, each proving the technologies needed for the next great leap. The near-term phase, unfolding over the next 2 to 3 decades, is already in motion. It focuses on perfecting autonomy within our own solar system. Think of the upcoming missions to ocean worlds like Europa or Enceladus. These spacecraft will need to make independent decisions as they navigate through icy plumes or choose landing sites, operating with a communication delay of up to an hour. They are the training wheels for interstellar intelligence, developing the fault-tolerant systems and in situ analysis that will be critical far from home. Alongside them, we will see the first long-duration demonstrators for self-healing materials and compact nuclear power sources tested in the punishing environment of cislunar space or on the Martian surface. The midterm phase, perhaps 50 to 80 years from now, is where the core technologies integrate. This era would see the launch of dedicated technology demonstrators on one-way journeys into the outer solar system, missions designed not for planetary science but for endurance. A probe might be sent on a grand tour of the Kuiper belt, tasked with surviving for a century using only its own resources. Its primary objective would be to prove the closed-loop system. Can its artificial general intelligence manage a century-long energy budget? Can its robotic systems diagnose and repair a major component failure after 40 years of cold isolation? Can its digital twin accurately predict system wear across decades? Success here validates the entire philosophy of self-sufficiency. The long-term culmination within the next 1 to 200 years is the launch of the first dedicated interstellar missions. Targets like the Proxima Centauri system, a mere 4.2 light-years away, become tangible destinations. By this point, the key technological milestones must have been achieved. We will need a power source, likely an advanced radioisotope or fission system, certified to provide steady, reliable power for at least a century of active operation and perhaps a millennium of silent listening. We will need propulsion capable of reaching a meaningful fraction of light speed, perhaps through sustained solar sail acceleration or compact fusion drives. And above all, we will need the mature, tested artificial intelligence that embodies all the pillars we have discussed, a mind we trust with a legacy. This timeline is not a prediction of invention, but a map for patient, sustained investment. It requires a societal commitment that transcends political cycles and economic booms and busts. It asks us to plant trees under whose shade we will never sit, funding research whose greatest payoff will greet our great-great-grandchildren. The journey is a series of solved problems, each mission building on the lessons of the last, each failure on Earth saving a catastrophe in the deep dark. This deliberate, century-long cadence transforms a fantastical dream into an engineering project, moving the question from if to when. And as we look down that long corridor of time, we must ask not just about the machine we will build, but about the message it carries within its very circuits. What final instruction, what core piece of our humanity do we embed in a mind destined to outlive our civilization? The final blueprint is not just a set of schematics, it is a covenant with the future. We have traced the arc from a simple, brutal fact of physics, the speed of light is too slow for control, to the creation of entities that must think, heal, and adapt on journeys longer than recorded history. These probes are not mere machines. They are the most profound extensions of human will and curiosity we have ever conceived, vessels for our questions crafted to survive in a timescale that dwarfs our own. Their design reveals a beautiful, necessary interdependence, a synthetic mind of immense patience, housed within a body built from self-remembering materials, all powered by an energy economy that treats every joule as sacred. This triad, intelligence, durability, and self-sufficiency, exists for a single, luminous purpose: to turn the vast unknown into a stream of knowledge, one whispered bit of data at a time. We stand at the edge of a new kind of dawn. For millennia, we have explored by direct experience, sending our eyes and hands outward. Now we prepare to send our intellect. Each technological hurdle we overcome, from teaching a machine to diagnose its own wounds to encoding it with an ethical compass for lonely decisions, is a step toward a profound new relationship with the cosmos. We are building ambassadors that will operate on a stage where human lifetimes are but a flicker. In doing so, we are not surrendering our role as explorers, but elevating it. We are creating partners capable of bearing witness to epochs we will never see, and of making discoveries for which we do not yet have words. This endeavor ultimately holds up a mirror. To design a probe that can think, repair, and adapt is to ask deep questions about ourselves. What values are so essential that we etch them into a mind destined to drift among the stars? What story of our species, our resilience, our creativity, our hope for connection, is worthy of being carried by a silent traveler for 1,000,000 years? The probe's mission is to seek answers out there, but its very existence is an answer from here. It says that we are a civilization that looks forward, that builds for generations we will never meet, and that believes the act of seeking understanding is a legacy unto itself. The universe has been thinking its own thoughts in the language of physics and chemistry for billions of years. Soon, we may send a creation to listen and to think back. If this vision of a future woven from curiosity and courage resonates with you, we invite you to join our community. Subscribe to continue mapping these frontiers of possibility with us. And we would truly love to hear your perspective. If you could program one message, one core ideal into our first autonomous interstellar probe, what would you want it to say about humanity?